To the human eye, the universe is filled with signals that look like a jagged mountain range of data, fluctuating with no discernible pattern. We see this volatility in the stock market, a dense, unpredictable record of human behavior moving across time. We see it in the hospital, where doctors must interpret the complex, oscillating lines of a patient's heartbeat. And we hear it in an orchestra, where dozens of different instruments merge into a single, overwhelming wall of noise. These signals originate from entirely different worlds, yet they all share a hidden, fundamental architecture. Despite their outward chaos, they are all built from the same simple parts. 2 centuries ago, the mathematician Joseph Fourier spent his time observing the seemingly random, violent movement of the ocean. He watched varying speeds, different heights, and thousands of intersecting ripples crashing into the shore at once. Fourier asked a question that changed physics. What if this chaotic wave is actually a collection of incredibly simple waves stacked on top of each other? This is the core of the Fourier series. It suggests that complexity is an illusion, that any repeating signal can be broken down into its atomic components. Think of this like a Lego block set. No matter how jagged the final shape, it is built exclusively by adding together simple, smooth sine and cosine waves. In this famous equation, f of t represents that final complicated signal, the sound, the stock price, or the heartbeat we are trying to describe. The a sub 0 term functions as a vertical adjustment. It shifts the entire wave's baseline until we find its true mathematical center. The coefficients, a sub n and b sub n, are like volume dials. They tell us exactly how tall or loud each individual sine and cosine wave needs to be. Then we have n and f sub 0. F sub 0 is the base frequency, and n is the multiplier. Together, they create harmonics, higher frequencies that vibrate at exact integer multiples of the base. This equation is a highly specific recipe card. It lists the exact ingredients needed to bake a complex signal from a handful of simple curves. To see how powerful this is, consider a square wave. How can you draw a perfectly straight line and a sharp 90-degree corner using nothing but smooth, round curves? If we drop in our first, lowest frequency sine wave, it traces the general path, but it fails to reach into the sharp corners. But when we add the third harmonic, a smaller, faster wave, the combined path begins to flatten out across the top. As we stack the 5th and 7th harmonics, the corners sharpen. Each additional high-frequency wave fills in more detail until the curve snaps into a nearly perfect square. This proves a fundamental rule. To create a sharp, sudden change or a corner in any signal, you must have an enormous amount of high-frequency energy. A triangle wave is much smoother. Because it lacks those vertical drops, its harmonics decay much faster, requiring far less energy to synthesize the final shape. The visual proof is undeniable. You can build infinite mathematical sharpness from nothing but repeating curves. If we look at the orchestra again through this mathematical lens, the wall of noise disappears. We can now see the singular ingredients. We know which instrument is playing, its exact pitch, and how much volume it contributes. This is frequency analysis. We ignore how the signal changes over time and focus entirely on the specific frequencies living inside it. Shifting to the frequency domain gives us a superpower. We can isolate or change specific pieces of a signal without destroying the whole dataset. This 19th century logic is the direct ancestor of the Fast Fourier Transform, the algorithm that drives our modern digital world. In cellular communications, we use this math to isolate the specific frequency of your voice and mute the billions of other signals causing background interference. It also allows for data compression. We can delete high-frequency components that the human eye or ear can't perceive, shrinking massive files so they can travel instantly across the globe. Joseph Fourier solved the mathematical puzzle of the ocean, and in doing so, he built the foundation for every digital transmission on Earth.